Hello, class. This is Mr. Sutton. I'm going to talk through the notes here to try to explain some things to help you get a better understanding of this material. Since we won't be there in person today to go through the notes. So first, I'm going to explain this activity that we would have done in class. Basically, there was a paper that we had with a circle on it, and you wanted to draw a line that passes through the center of the circle and then label the points on the diameter A and B on each edge of the diameter. And then, so how many degrees are in the half circle from point A to point B? That would be 180 degrees to go halfway around the circle, and then 90 degrees to go around the quarter of a circle. And then, so starting at point A, moving clockwise, we want to mark the angle measures for each quarter of a circle. So it would be 90 degrees, 180 degrees, and then 270 degrees, and then 360 degrees to go all the way around. And then we cut some pipe cleaners instead of Twizzlers to be the length of the radius. And then we want to place one end, we want to take that radius length and place one end at A, and then wrap it around the edge of the circle to see how far it goes around the edge of the circle, and call that point C. And then we wanted to measure that angle from the center of the circle out to points A and C. So O being the center, so A, O, C, that angle. Which should be about 57 degrees, 57.3. And ideally, if everyone did it right, they would all be the same. And then the length of the arc, that depends on how big the circle is. So it wouldn't necessarily be 10 centimeters in our case. And then we want to keep wrapping the radius around the arc of the circle. And so how many Twizzler arcs, so these are radius lengths, would wrap around half of the circle? So starting at point A, wrapping around to point B, you should have just over 3 radius lengths that wrap around halfway. And really what this number is pi. It's 3.14159.265. And then the number of radiuses that go all the way around the full circle, so halfway is pi. To go all the way around from point A to point A again is just over 6. Really what this number is 2 pi. It takes 2 pi radius lengths to wrap all the way around the circle. Which brings us to the circumference formula. Circumference is 2 pi r, right? So it is the number of radiuses, or it's the length of the radius multiplied by 2 pi gives us the circumference. So no matter what that radius length is, to determine the distance of the circumference, you multiply it by 2 pi. I'm sure we all know this formula, but have never really thought about what it means in the context of the actual length of the circumference versus the radius. So whatever that radius length is, if you multiply by 2 pi, you get the circumference. So what does the circumference tell you about the radius arc lengths? It should fit around the circle, so it should be 2 pi radiuses that fit around the circle. And then how many radius lengths should fit around half of a circle, around a quarter of a circle? So around half of a circle, it should be pi, like I said up here, right? Just 2 pi divided by 2. And then around a quarter of a circle, you would take pi and divide by 2 again. So it'd be pi over 2 radius lengths to fit around a quarter of a circle. So why are we talking about this? We are talking about radians today. So that is how radians are measured. It's based off of the length of the radius and how many radiuses could fit going around the circle. So this is the general idea. 90 degrees is pi over 2 radians. 30 degrees is pi over 6 radians. 45 degrees is pi over 4 radians. So this is our circle here that has all of the conversions from degrees to radians. So going out straight to the right is 0 degrees, and then we move counterclockwise. So angles on a circle are measured from the positive axis counterclockwise in degrees or radians. So going out straight to the right is 0 degrees, and then 30 degrees or pi over 6 radians is up here. So moving counterclockwise, and then every 30 degrees beyond that is an additional pi over 6. So 60 degrees is 2 pi over 6, which simplifies to pi over 3. And then 90 degrees would be 3 pi over 6, which simplifies to pi over 2. And then 120 degrees is 4 pi over 6, which simplifies to 2 pi over 3. And then 150 degrees is 5 pi over 6. 180 degrees would be 6 pi over 6, which simplifies to pi. 210 degrees is 7 pi over 6. 240 degrees, 8 pi over 6, which simplifies to 4 pi over 3. And then 270 degrees would be 9 pi over 6, which simplifies to 3 pi over 2. 300 degrees, 10 pi over 6, which simplifies to 5 pi over 3. 330 degrees, 11 pi over 6. And then finally 360 degrees would be 12 pi over 6, which simplifies to 2 pi. So that covers counting by 30 degrees. We can also count by 45 degrees. So a 45 degree angle is pi over 4, and then an additional pi over 4 for every 45 degrees beyond that. So then 90 degrees would be 2 pi over 4, which is pi over 2. And then 135 degrees is 3 pi over 4. 180 degrees is 4 pi over 4, which simplifies to pi. 225 degrees is 5 pi over 4. 270 degrees is 6 pi over 4, which simplifies to 3 pi over 2. 315 degrees is 7 pi over 4. And 360 degrees is 8 pi over 4, which simplifies to 2 pi. And then finally counting by 90 degrees, we have 0 and then pi over 2. And so every 90 degrees beyond that would be another pi over 2. So this is 2 pi over 2 for 180 degrees, simplifies to pi. And then 270 degrees, 3 pi over 2. And then 360 degrees would be 4 pi over 2, which simplifies to 2 pi. Negative angles are measured clockwise. So if you get something that says negative pi over 2, then rather than going clockwise to pi over 2, you're going in the negative direction, which is clockwise. So negative pi over 2 would be 90 degrees clockwise. So that would be equivalent to 270 degrees counterclockwise in positive direction. So that would be this angle measure here, positive 3 pi over 2. And a radian is the measure of an angle whose arc length is 1 radius. So 1 radian is about 57.3 degrees, which is where this number came from here. Another thing I want you to write down is the general conversion from degrees to radians. So to determine the number of radians when given degrees is you just take the degree and then multiply it by pi divided by 180. And you want to usually leave it as a fraction in terms of pi. So here's some examples, like 120 degrees. You multiply by pi divided by 180, so you'd have 120 pi over 180, and then you want to simplify that, so you would divide by 10, cancel out the zeros, and you'd have 12 over 18, and then you could divide by 3, so then you would have 4 over 6, or, well, 6 would probably be better to divide by, right? Yeah, because 6 goes into 12 and 18, so then you'd have 2/3, so it'd be 2 pi over 3. Same thing here, 30 degrees times pi divided by 180. So that would be 30 pi over 180 radians. And then, so 30 is into 30 and 18. So that would be just pi over 6 radians, right? which matches what we had. Our conversion here, 30 gives us pi over 6 radians. So that is the general way we convert from degrees to radians, is you multiply by pi over 180, and you want to keep it as a fraction in terms of pi. To go from radians to degrees, you take the number of radians and multiply it by the inverse of that. So 180 over pi, so the pi's would cancel, and yeah, multiplying by 180 would get rid of the 180 in the denominator as well. And then, so some other things I want you to write in your notes, arc length formula for degrees. In the homework, there's some questions about arc length. So to find the length of the arc, when using degrees, the formula is 2 times pi times r times theta over 360, where theta is the measure of the angle, the central angle of the arc in degrees. So that is the arc length formula when using degrees. The arc length formula when using radians is just the angle measure in terms of radians multiplied by the radius. So it's a lot simpler, which is why radians are used in mathematics, because the math is a lot simpler, because radians have more mathematical meaning because it's based off of the number of radiuses that wrap around the arc rather than based off of some 360-degree counting system, which the 360 degrees is more arbitrary. It's used mostly because 360 can be divided by a lot of numbers, and because in ancient Babylonia they thought there were 360 days in the year, and so they thought that number was more significant than maybe it is. But radians have more mathematical meaning, and they make our formulas a lot more simple. So that is why we use them.